Hello. I don't know if you hear me online.
Hello, I can't hear you. Yeah.
Okay, good. So let's start. Good morning, good afternoon, good night for some of you who are online, and bonjour for those who are attending physically the conference. I'm really happy on behalf of the conference chairs to welcome all of you to the 23rd National Conference on Web Information Systems Engineering. Well, as you know, this conference is in hybrid mode. So some of you are online, and I hope that you hear me well. Now I would like to give the floor to Professor Yanshun Zhang, our General Chair, to introduce WIRE. Yanshun, you have the mic. We don't hear you. You have to switch on your microphone. No. Can you switch on your microphone, Yanshun?
Okay, I can speak now. Yeah. Okay. Good morning. Good afternoon. Good evening. Actually, it's later evening in my place. I think it's in the afternoon in France. So good day, good evening, good morning, everyone. We have participants all over the world with different time zones. So welcome you all. I'm Yanshun Zhang, General Co-Chair of WISE 2022 and the Steering Committee Chair of WISE Conference Series. So welcome to the 23rd International Conference on Web Information System Engineering. This is the 23rd event of the conference series. It was first started in Hong Kong in 2000. Our aim was to develop an international forum for exchange research results in web and internet technology and applications. Then it went to Kyoto, Singapore, Rome, New York, Brisbane, Australia. This is the 8th time in Europe. It had been in Nancy, France, Rome, Poznan, Cyprus, and Greece, and Amsterdam. And now it's mixed mode. It's in Basel, France. I hope I could join you there, but somehow the border still closed here. The topic of this year include web internet technologies, cloud computing, blockchain, AI, big data, and applications. I wish to take this opportunity to thank our organizing committee, especially my co-chair, Professor Yanis Manolis, and 3 PC co-chairs, Richard Chibel, Professor Helen Huang, Fabrizio Silvestre, and our other organizing committee members and volunteers. Most importantly, I would like to thank the authors and the participants for your support to the conference. The conference has a very high quality program with 4 world-renowned keynote speakers. I wish you all enjoy the conference. Besides the conference, when we developing the web conference, we have also developed a journal, World Wide Web, a www journal. This is a well-known journal in internet and web technology. This journal accommodates one special issue each year for selected web conference papers. The author of selected papers will be invited to submit extended version to www journal. Now I will pass the floor to Professor Richard Chibel, our PC co-chair, to introduce the program. Richard, I pass the floor to you now.
Thank you, Professor Yanshun, for this introduction. WISE 2022 is now in Beirut City for those who are attending physically. This morning we had the excursion with some few of you who attended, and I hope that you enjoyed the excursion in Beirut's downtown. The conference venue, I don't know if you had the time to explore booklet that we sent to you. The conference venue is a Novotel building, the other building just next to this one. Since today we are in maintenance phase, this is all for us for the whole day. Just keep an eye on this plan, because tomorrow we will move to the other building for our sessions. Okay. Just I would like to represent again our conference chairs, Professor Yanchun Dong, Yanis Manolis, who gave us the pleasure to be on board. I was happy to co-chair the program of the conference with Eleni Wong and Fabrizio Silvestri. They are not online, but they will be attending some sessions today afternoon and tomorrow. I would like also to present our tutorial chair, Vasilis Christofi. I don't know if he's online. Maybe he will be online the afternoon, since we will have our tutorial. And we have two chairs for the demos. We have Joe Tekli and Apostolos Papadopoulos. Thank you guys for your support. This is the first time for me personally to manage a conference with the diversity and inclusion section. So this year we had two chairs for diversity and inclusion, Wani Rahayu and Sana Salami. Their inclusion impacted the conference program, and you will see that later. I would like also to introduce other chairs of the conference, the workshop chairs, Mira and Hua Yang, the publicity chair, Shiyu Yang, the publication chair, Karan Shaya, who is here, and our webmasters, Eli Shisha, who is here also behind you, and Eli Mansour. I would like to say some words about our statistics. This year we got a total number of 100 submissions that they were distributed over 25 countries, with, of course, a big participation from China. 44% of the submissions were coming from China. A big also percentage from Australia, and of course in France, since the conference is in France this year. Also some statistics about the submissions and the acceptance, as you can see on this figure here, and also about the countries. Out of all the submissions we received, we accepted 30 as regular papers, 14 as short, and 3 as remote papers. And what is interesting is that most of the papers were located from those countries that you see on the map. It means that the distribution is not really normal between submissions and the acceptance. So yeah, most of the papers were located, the accepted papers, in let's say 7 countries, no more. I would like to highlight the international facet of the program committee of WISE 2027. Since this year we had 149 members, which is pretty big. And they were coming from 30 countries. And they did a great job to review your papers. Since I put the table here to show you the numbers about how many reviews each paper got during the peer review. So most of the papers got at least 3 reviews. So this means that the selection was really good. But of course, it's wide, and we wanted to maintain some some standard. This year, the topics of WISE were distributed over 12, let's say, topics: social media, spatial and temporal issues, query processing and information extraction, architecture and performance, spatial data processing, security and privacy, information retrieval and text processing, reinforcement learning, learning and optimization, graph data management, recommendation, and neural networks. And those, you can see them within the program that was shaped like this, as you noticed on the website. And today we're gonna have our first keynote, and then we're gonna have our tutorial. And tonight at 7, we're gonna meet again here in this space for our welcome reception. Tomorrow, as I said before, we're gonna move to the Novotel building for our second keynote. And then we're gonna be divided into 2 sessions, 2 parallel sessions until lunch. Then we will have again our keynote speaker, third one, dedicated for diversity and inclusion. And then 2 parallel sessions, 1 session, and then 2 sessions, sorry, not parallel, the afternoon. And at 7, we will move to our banquet. A bus will be waiting for you in front of the hotel. Okay, so we will be driving you to the place, and we will be bringing you back to the hotel afterwards. The last day will be hybrid. It will be fully online. So there is no room, no space to attend. So you can do that from your room for those who are attending physically, and those who are online, you are already online. So feel free to do that as per your convenience. Okay, for the rooms at Novotel, you will be following the rooms Gitari and Bidar. But in any case, you will be guided. We will be there tomorrow, so no worries about this. Coffee break will be located nearby. So this afternoon, the coffee break will be just behind you, and then we can just share it outside. And during the coffee breaks, we will play some videos for those who are attending online to share with you some tastes of the areas. For lunch, tomorrow also we're gonna be, as I said, in Novotel, so we will use the restaurant of the hotel. That's it for the organization. I've been notified that the proceedings will be published online on November 7th. So once I will be notified, then I will inform all of you. As Professor Yanshun mentioned, we will be organizing 2 special issues after the conference. One will be dedicated for the journal WWW, and the other one will be organized within Data Science and Engineering Journal. Both of them are published by Springer. Okay, now I would like to thank Springer and LNCS for their support, since WISE is always published by Springer. I would like to thank my university, Université de Pau et des Pays de la Dour, and more particularly the excellency label of our university that we obtained in 2018, E2S. It is focusing on energy and environment solutions. Many thanks to our keynote speakers, Marco, Flavius, CM, she will join us tonight, and Athena will be online with us on the 3rd day of the conference. Thank you for accepting to share your experience with us. As I mentioned before, diversity and inclusion this year led us to do some different strategy in organizing our session chairs. I would like to thank them all. So we got some equilibrium between men and women. So we have 7 men and 7 women that will be sharing our sessions. Thank you again for helping. I would like to thank again the conference chairs, the program committee members who did a great job, and the reviewers, the external reviewers as well. I'm not gonna forget the local organizing team, Open Sense, that you see here. So some of you saw few of them during the excursion this morning. Yeah, this conference couldn't be possible without their support. Some of them are online also because they couldn't attend it physically. Thank you guys for everything and for the support all the time. Lastly, I would like to thank again all of you. I hope that you will have nice moments of scientific exchange during WISE 2022, and you will leave this event enriched with new ideas, collaborators, and friends. Thank you very much. Merci beaucoup. I hope I was not long. Now I would like to declare the conference open on behalf of the conference chairs, and then I will give the floor to our first keynote speaker, Michael. Michael, if you will. I'll give you some few seconds to prepare your laptop, and then I will say some things about you. Okay. Yeah, I have to change my glasses.
Why don't you just only sharing from here?
Yes. Okay. Marco Brambilla is a full professor at Politecnico di Milano. He is an active researcher in research and innovation, both at industrial and academic level. His research interests include data science, software modeling languages, design patterns, crowdsourcing, social media monitoring, and big data analysis. He is co-founder of the startup Luxudo, focusing on social media analysis, big data, and social engagement, and of the company Web Ratio, devoted to software modeling tools for web, mobile, and business process-based software application. He's author of many papers, let's say more than 200 papers, and he wrote 7 books and many scientific articles for conference central. Impressive. He contributes to various standardization initiatives with OMG and WCC. Well, his CV, even if it's we asked them to have a short biography, is long.
Whatever you like.
I would like to say that also he's member of Stereo Conference and Workshop, member of the committee, and he has been reviewer for many scientific journals. He is associate editor of Signal Records, and today's talk is about exploring the barriers, how to analyze and benefit from the digital and physical ecospheres. So I'm really excited to listen to you.
Okay.
Thank you.
Thank you. Thank you, everyone. I'll switch on my camera. Let's see if it works. And maybe you can even see me from home. All right. So, great. Okay. So good afternoon and thanks for being here. I decided to go for this topic of exploring the biverse, which is a word clearly invented by me just this morning. No, just when Richard invited me. So first of all, thanks Richard for the invitation and the committee members for this. Why? Well, because we have been hearing a lot about the multiverse and whatever, and the drop in value in large web corporations and so on. But my claim is We are not ready yet for multiverse. We are not even ready for the biverse, that is the duality between the physical and digital world. This is the main thesis of my talk. It won't be an academic talk. I would like to give you some perspectives on my experiences that go across, as Richard mentioned, across the academic and industrial ecosystem, and try to somehow condense some learning experiences here. I guess you will perceive this, and you will probably somehow find some commonalities with your experiences as well. I hope so, at least. So what are we going to talk about? First point is, how is the role of, say, web information system, web science, data science perceived in general society and economy? Well, as scientists, as researchers, we typically focus on one point, that is, we want to measure, we want to build models, we want to design things that capture phenomena. But the thing we miss is that we cannot stop at measuring and analyzing things. Companies, economy, and society expect that out of what we do, we are able to generate value. If we can't go to that point, we are totally missing the point, actually, because we cannot enable this virtuous cycle to run continuously. So in this perspective, I would like to mention a few challenges, a few things we need to consider when addressing this long-term continuous cycle. First thing is, let's not forget, we are working in a complex environment. So whenever we do things, let's remember we are not running an experiment in a lab with a controlled environment where everything is set and under control. So I start from a popular citation. This is one of the authors with the highest H index in the world, I guess. So William Shakespeare actually said at some point, there are more things in heaven and earth, Horatio, than let me stretch it a little bit, that we can model, design, and represent with our solutions. Okay, so what's the point of this? Well, the point is we need to take a little bit of a humble perspective on reality. We cannot expect that we build solutions that will address all the complexity paradigms. So once we do that, we need to realize that whenever we start collecting data, we have a very small, a very limited understanding of reality. So that's why we need to move on, okay, towards the big answer to life and whatever, which is not 42, as someone say, but it's a little bit more, maybe it is, but this came out of a long journey towards wisdom, because we need to move from raw data, from data-driven approaches to information and knowledge-centered design of solutions. This means raw data gives us limited understanding, gives us very detailed perspective on only few limited contexts, and we need to move up through the ladder to understanding relations, patterns, principles, and that's the only way we can make sense of reality in its complex combination of ingredients. So life is complex, we all perceive that. Reality is complex, but the thing is, Shakespeare also gives us another hint on how to solve it. That is, we have actually two words, the biverse I was mentioning, that intersect, overlap, and somehow reflect each other. Because we live in a physical world that is somehow reflected into a digital ecosystem. And this reflection is actually bidirectional. What happens in the physical world today is reflected in the ecosphere of the digital web, social media, blogosphere, and so on. And sometimes things happening up there reflect on the physical world. So this is something we need to reflect whenever we launch our web science analysis, data science analysis. What is the relation between the two? And why is it so interesting to build social media analytics? Well, the thing is, we do that because the digital ecosystem is much easier to monitor and analyze than the physical system. So we use the social media than whatever else you want to use, simply because we want to understand the real world, let me call it, and since going here is so hard, we resort to using that to understand the bottom part. Okay, so and the thing is, actually, this reflection is getting better and better every day. Our life is built over traces of things we do, and these traces are getting more and more detailed in the digital ecosphere, and these traces are left now and forever in the digital ecosphere. So clearly, I don't need to tell you, if I could trace every digital trace you leave online or on whatever digital system, from credit card to your smart car to your whatever thing you have, okay, clearly I can understand a lot about your life. And clearly, this is much more informative than 10 years ago, 20 years ago. Our parents, well, our grandparents had zero digital impact, right? So what happens today? And this trend is continuing. So we can actually exploit this for our analysis. And this is interesting and visible in many, many settings where these reflections are concrete, practical, quantitatively assessed. For instance, this one is a study from 2010, shows the relation between the sentiment on Twitter and the poll on consumer confidence in the US. As you see, you have very clear correlation between the two signals. And as you see, probably even more interesting, these parts here show that social media sometimes could be predictive of what happens in real life, because social media are, in some settings, are more reactive, are more dramatically reactive to phenomena. So things that in real life, maybe trends that happen slowly in the physical world, sometimes have a strong reaction in the digital world that can let us anticipate phenomena that we will capture in the physical world later, especially negative messages, right? We are aware of that. This is another example. This is a study we have been running for several years, the monitoring of the Brexit process on the digital ecosystem. Clearly, there is a reflection between the physical and digital world. The day of referendum, and you see the drop in presence of supporters of the Brexit process just a few days after. You can monitor this in terms of trends, and thanks to the digital space, you can monitor this down to the individual, the single individuals. Here you see, for instance, how many people change their perspective before and after the referendum of the Brexit process. You see here, the people that before the referendum wanted wanted the Brexit to happen, and you see a good share of them changing their choice after the process started. And this also reflects in real numbers, digits. Another example is this, where you can compare the role of the digital space with the physical one. The studies we've been running was comparing disinformation online with adoption or rejection of COVID vaccination in different regions of Europe and Italy. Okay, this one is the picture for Italy, but you have here the links to the other platforms. So here you see region by region, area by area, how online disinformation actually affected acceptance of COVID vaccination in the same regions. And there's a strong correlation in some regions, actually. So there is actually a reflection between these two ecospaces, digital and physical, and this is quantitatively assessed through many experiments we may run. Second point, if things are so complicated, so complex, what are the tools we can apply for making them simpler? First thing, and may come also from a bias of my background, first ingredient is modeling, okay? Whenever you have a complex ecosystem to describe, it's really good to start building a model. A model that is a simplified view of reality according to your purpose and your scope. So you start modeling reality, understanding things, and just let me make an example. Suppose you want to monitor and analyze a complex reality, even at a large city scale or a large economical phenomena or social phenomenon. Okay, I will start with a city-wide example. You want to model a city, it's complicated. Okay, let's start from a model. You model things, you model stuff that you feel are relevant. Okay, so your city is classical statistics, locations, people moving around, and actually what people do in these locations, what they say, how they are related with each other, and so on. So the model is good because it lets you focus on things that are strategic for your study. First ingredient. Second ingredient, the multi-perspective strategy. Whenever you have a complex ecosystem to analyze, you need to apply the right tool. I'm not talking about technical tools. I'm not talking about using this or that library or this or that technique. This picture, it's taken by a fairly old book called The Macroscope. And it's not from data science or anything. So the thesis of this work was that as observers of reality here in the middle, okay, humans had the good, okay, they evolved and became able to build instruments, tools, and also tools for exploring reality, not just physical tools. So you want appropriate tools for exploring big, small, but also complex things. So whenever you need to explore a complex thing, society, nature, economy, business, whatever, you need a tool that has specific features. And this tool, I mean, this guy back then in 1979 had this idea of a tool called the Macroscope. It was not a physical tool. It was not actually an implemented tool. It was just an idea. But today we can build it. It's what we build whenever we run comprehensive data science analysis. So the idea of the Macroscope, okay, the book, it's a full book, so you can go and read it. But among the main features of this Macroscope thing, you have the idea that to explore complex things, you need to have multiple perspectives on these things. You cannot observe something only from one direction, only from one perspective. Otherwise, you will miss something. I mean, you will still miss something, but maybe you will miss less. Okay, so the Macroscope is a tool built of many lenses that let you perceive reality from multiple perspectives. And this is the second tool. So what does it mean? Well, it means that whenever we are asked or we want to run an analysis, we cannot simply say, okay, I have a nice neural network model. Oh, I have a good classifier. That's not it. This is not the purpose. This is an exercise. If you want to run a comprehensive analysis that builds value, you need to have a multi-perspective. For instance, this study here is a study that was built for analyzing the impact and perception of the design ecosystem in Italy, especially in Milan. And the first point was, are people happy about what is shown in this ecosystem? The quick answer would be, okay, let's run a sentiment analysis. Let's see, are you happy? Are you not? And that's it. So you realize, yeah, okay, I have a few people that are happy about this place or these kind of events. But that's not enough because you don't understand what's happening. So the multi-perspective view is, sure, you run sentiment analysis, but you also need to run an analysis on who are the people that are talking about this. So you need to understand provenance, who are the prospective users or customers, or maybe in this case, this is a city study, where these people are going, depending on where they're coming from, or what they are talking about. This one is entity linking and semantic analysis, topic analysis. And you need also to understand profile and segmentation of your people. Once you get to that point, so in this case, for instance, clustering of users, understanding the different profiles and so on. Once you get to this point, you start understanding something because you then combine these perspectives and you see, are people loving arts happy about your event or your brand? Because if you just run sentiment analysis, you have a general perspective which is not bringing any value. Why? Because you may collect data from people that are not relevant for you. This is the thing. Clearly, you can run classical demographics and so on. And then there is another problem though. Complexity is one thing, and the other thing is typically when you study things, you just realize the obvious. I'm saying this because in many cases, companies or let's say institutions come and say, I would like to run some kind of analysis because I want to discover new surprising things. Okay, this is what people perceive, right? How data-driven strategies will let us understand incredible things. Well, the thing is, most of the time, most of the strategies will find obvious things we know already, or things that somehow are just confirmed by our analysis. It's not bad to have a quantitative assessment of something you somehow intuitively anticipated, but don't expect necessarily to have surprises. Why? Because finding new things is really hard. Actually, especially when you have a massive amount of information, it's much easier to find what we call high frequency ideas, high frequency concepts than the long tail. Why? Because even the web and the way the web is built and the way the web applications built on data analysis are built for making the high frequency part emerge. So finding new surprising things is really hard, okay? We need to make aware, well, first ourselves, but also our stakeholders that this is the case. And even if we try to make things emerge, we need to cope with an important point. That is, we are all humans. And whenever we run an analysis, we somehow always inject some kind of cognitive bias. So we run things to try to obtain what we want. We run things that confirm what we think. We run analysis that we build based on our previous knowledge of technologies, context, and methods, okay? So keep it in mind. Basically, what's the point? We typically look for what we search only where we can find it, or where we can search for it, even if it's not there. So that's the trick of the street lamp effect. So we need to be careful when trying to find things that we need to combine availability of data, capability, technical capabilities we have, and the risk of going in directions that are not describing reality, but they are describing ourselves. That's the point. Along the path, we have another issue, that is, we also need to make sure that the quality of our results are good, right? I mean, as researchers, we typically focus more on this than on the previous problems. So we start looking at techniques and we analyze, okay, our accuracy is improved, our precision is getting better, whatever. But improving quality is not only like that. Improving quality means that we need to start from the data, okay? This is a Garden study. 30% of global companies experience a problem with their data. They cannot trust their own data. And the biggest ones, I'm not talking about the corner store or whatever. The biggest companies in the world do not trust their own data. Can we trust our own data? Considering we are grabbing it from the web, social media, scrapers, how reliable it is. That's the point. And then clearly we play with data, right? And we know if you torture data enough, it will confess anything. So let's make sure that we don't combine our cognitive bias with limited availability of the data, with limited understanding of the domain, and we end up with a totally useless result. That could even be misleading, okay? Now, again, from a research perspective, sometimes we lose sight of this because we end up with a paper. Once the approach is sound, once somehow we convince the reviewers, the paper is accepted. But once you have a company that needs to run over the data and over the analysis you have provided, then you realize whether you are actually generating value or not, because the company is going to fail if you give them the wrong results, okay? And wrong means wrong in many different ways, okay? From let's say, from an instrumentation and architectural perspective to a technical perspective. This one is a very basic thing. Here you see a collection of data about participation to public events, nightlife events in time, okay? Here you see some highlighted areas that are the weekends, and the expectation is that, well, probably a lot of people will join events in the weekends, right? So if this is a cumulative trend, we should have peaks during weekends. But then here we are. We have a totally empty thing here that is not a lockdown weekend for COVID, but it's a simple fact. People building the information system for data collection and processing here didn't build it with enough care. So in that weekend, the information system went down. And nobody realized that until next Monday. You see, Monday morning, you have a peak. So either everyone goes out for a drink on Monday morning, or we have a technical issue on the architecture. So as information system experts, we should also consider that the impact of the systems we build will actually affect the analysis. And because if they affect the data, they will also affect the analysis. This is an example, but there are plenty of others. How do we transfer the understanding of what's quality in data analysis? Because this is the next step. Again, people misunderstand sometimes what's the meaning of the analysis. In this picture, you see an analysis that was run real time in the popularity of hotels in Milano. And this picture, I went back and picked it from a long time ago. You see, it's a 2015 picture. Why? Because in 2015, we had in Milano the Universal Exhibition, okay, the Expo. And that was something that somehow changed completely the dynamics of the city. What you see here is the trends in hotels' popularity. And now I'm not sure you can read it, but what you see is that you see basically at the opening of the event, which is May 2015, you see a complete switch in the dynamics. You see hostels, middle to low range hotels going down in popularity, and you see extremely luxury hotels going up. So this is a trend. This is a setting that is changing the dynamics of the city. And you wonder, okay, so if I tell this to a businessman, what will he understand? Now, he will understand that I'm showing hotels by number of customers, occupied rooms, right? We need to make them perceive that if we run web analytics or web analysis, we are at a different level. The reflection between the digital and physical world are not perfect. They're not the same thing. It's not a perfect mirror. So here we see this trend, which is a trend, it's definitely true, but is not the number of customers in hotels. This is popularity of hotels online, which is different. It's a trend, it's saying something, but at a different level of quality. On the other side, you have a big advantage, that is, you have this data in real time, by the minute, if you want, okay, day by day. Okay, so this is the increasing trends over the luxury hotels. So in terms of quality, we are talking about data and questions. Are we responding to the questions we are asked, or are we making up our questions so that we are ready to give the answer? That's the point. We will talk about that at the end of the talk. Okay. For instance, again about the city. I'm showing you a few pictures now about the dynamics of the city. Again, I pick Milan, where we have been running a lot of analysis. Here you see check-ins of people in the city. What do we have here? A typical example of obvious results. We have a huge amount of people going through the airport and the central station in the city. Well, no surprise here, right? Clearly, we have millions of people going through these places. Or maybe actually also going whatever to the stadium, okay, for Milan and Inter matches, or to the Milano Duomo Square. But is this valuable? I'm just stating the obvious. Where is the value in this picture? Well, actually, maybe the value is in the smallest bubbles here. So I'm playing a trick, showing a result for which I don't have a question. What am I saying? What am I responding to here? Other pictures. These ones are the density of photos in the city. 300,000 photos geolocated on the city. What am I describing here? Okay, by the way, in this case, taken from Flickr. You all know what Flickr is, right? So what I'm describing here is probably density of nice pictures by semi-professional people with nice camera, tourists maybe taking nice pictures. Next map, Instagram. 300,000 pictures, same number of pictures. These are not more pictures than the other, but with a totally different distribution. Why? Well, again, I don't need to state the obvious. Clearly, the audience is different. The use of the platform is different. But the problem is, if I take the wrong data source for the wrong answer, for the wrong questions, I'm going to give the wrong answer. Okay? So I need to be careful about what I pick as a data source and how I respond to the questions. Along this path, we have a further problem. That is, if we really want to build a multi-perspective view of a complex system, this means we probably need to build an integration of multiple sources, because we cannot trust one source. We cannot run an analysis on one source. So what can we do? We integrate multiple sources, fine, but integrating multiple sources brings in the problem of diverse granularity. So here, now, okay, I don't know if you see it also. Oh yeah, it should be animated. So what you see here is social media analytics run over a specific period of time, that is the Milan Fashion Week. And these are basically Instagram posts a few days before, you see until day number 8, I think, 7, 8, yes. And then here we start the events. The stars are actually the fashion shows in the city. And then, okay, the events finish, and then you have the long tail of the reactions. So clearly, each individual data item, as I said before, as a raw data source, has a very limited contribution to the understanding of the dynamics and has a very contextual description of reality. How can we make it a comprehensive description? Well, we need to transform this dynamics into something that can be integrated with other perspectives. So we need to create a comprehensive and consistent granularity across the data. In this picture, what you see is a granularity perspective over space by creating grids on the map, and time by creating a sort of a film where you fix temporal granularity so that then you can merge as many sources as you like for geographical and temporal dynamics. because at this point, okay, this is just the meta model describing that. I'm skipping it. At this point, whatever comes in, you can make it converge to the same granularity, and you can start running correlations, starting analyzing different perspectives, because even if they are different sources, you make them work all together on the same space and time model. Okay. Clearly, then different shapes can be defined, different timing can be defined. One important thing, typically, whenever you need to run analysis across, say, physical and digital spaces, is you need to run a multi-granularity analysis. So you work at city level, you work at lower scale level, you work at single point of interest level. So these different granularity levels imply different techniques. Well, first, different data sources, because at the broader level, you could use large scale sources, demographics, public data, telephone, cellular network data, whatever. Then, or social media, the broader sense. Then you zoom in and you start moving into more detailed data, geolocated web data, maybe sensors. And then you zoom in again, and you actually need, if you really need a physical local place, you need physical sensors. So in this example, you see, we go from large scale analysis. The picture with those squares you see is an analysis from cellular network providers, telephone companies that provide data of cell phones connecting to their antennas, which is by definition aggregated, anonymized, and with a very bad granularity level. And then you zoom in, you use social media, you use physical sensors. You see in this case, we use these 3D cameras from the top so that you didn't have any problems with privacy, but they are still able to monitor the flow of people, the direction of movements, and also correlate multiple flows across different locations. What's the result? Sorry, this is in Italian because this was provided to a specific customer. This is a screenshot. The result is an integrated analysis where you see up here how many people get in and out from the different entrances. In this case, this is the cathedral of a small city, Como in northern Italy. And this is the cathedral square. So you might say the most valuable locations in the city. So you want to monitor in detail. You see global trends, you see evolution in time, comparison with the normal behavior and the peaks, integration with APIs, providing, for instance, weather forecast, weather data, and also you want to understand what happens and why we have so much people in the place. And so you resort to social media analytics to understand things and so on. So if you don't have a multiple perspective, again, you may miss something, okay? In this trend, you go down and down until you reach the sensing part, that is the expensive part. IoT means you have to put things, devices around in the physical space. This is a summary of the typical use cases of a physical world integration with digital, okay? Which means that you need to bring together sensors and digital spaces. Let's take a consumer perspective on a very simple case on this. Because the perspective we have as researcher is always, yeah, we have plenty of data, we have a great data integration, the web is great, but let's take the consumer perspective. Suppose the consumer wants to build a smart house. I don't know, domotics, home automation, these kind of things. What's the perspective of the consumer of this? Let me rephrase. How many apps, how many websites, how many registration does the consumer needs to have to make his house smart? Because now there's a lot of hype, right? You just buy our digital assistant and everything will work smoothly in your house. Sure, except that you need to have clearly someone plugging in your house. So this is just one brand. Again, it's a capture in Italian because that's what I had by Legrand and Biticino brand from Legrand. So you want smart plugs, you want smart thermostats, whatever, good, go. Ask some companies to come and install them in your house and then put in your mobile app for this, right? But then, you know what? I would like to have nice lights. Yeah, you go to another provider. And again, is this compatible with the other? No. You need to buy things. You need to buy a separate hub. You need to install an app, different app to monitor that and to control that. And then you go on and on. Some things play as integrators. These guys here claim to be sort of integrators. But again, they integrate only a few things and only sometimes and only some features. And then if you have a different phone, you have a problem because you might have the Google Assistant at home, and then you have an iPhone that has Siri and it doesn't work with the other. And then you put Alexa in place, and that's crazy. And then you go on and for every new feature you want, you plug in new brands which require new apps or new registrations that do not work together, or sometimes they create problems with data integration, they create problems with compatibility, and also inconsistency, because you plan lights on an app, and then you plan temperature on another, and then there are automatic triggers that trigger one with the other, and the house gets crazy. So this is a very, very rough perspective of what should a smart house be, okay? And this is, again, a problem between digital and physical, because the ecosystem is not ready. We can somehow grab things from one place to the other, but it's really, really preliminary as a result, okay? Final point, access and value. How can we condense all this into something that is valuable? First problem is access. Who has access to the data? Some time ago, I don't know, 10 years ago, people were talking about the digital divide, right? Today, we should talk about the data divide. Who has the data and who has no data? Because this is becoming the distinguishing factor between success and failure. How can you compete with a company like Google or Amazon that has so much data, so much analytics, so much insights if you are a small business? And this is not just a technical problem, it's a societal and economic problem. There is another level, though, that is not only you need to have the data, you need to be able to use it. And that's another step again. Okay. Let me go quick here. So the point is, if we have our data and we want to build a decision and actionable decision process, what should we do? Well, we need to put in some analytics. Good. So sometimes it's just descriptive, sometimes it's predictive, what's going to happen. Sometimes it's diagnostic. It's trying to say why this happened. Think about all the explainability parts and so on. And you see that the trend is towards helping decision makers to take right decisions, up to the prescriptive step that is, I tell you what you should do. Or I really do and take the decisions automatically. Okay, this is not mine. This is a Gartner model. How does it map to our perspective of digital and physical world, and also our perspective as users of these dynamics? Well, it's not surprising. This happens every day in our everyday life, every moment. Every decision happening will be along this trend. And most of the time, we are seeing this moving from nothing. Okay, so we take autonomous decision to descriptive, diagnostic, and sometimes also fully automated. Our car now is able to brake without any intervention of the driver because It just detected some kind of obstacle in front, right? So that's full decision automation. So you need to build models that grab data from physical world, sometimes through other providers that are actually pure digital providers like social media, run analysis that go in one of these categories. And based on that, someone will take a decision on based on your analysis. So, I mean, in a way, we need also to have a certain level of responsibility in what we say, what we state in our studies, in our research, okay? Actually, most of the companies today are not looking from only for the top data scientists, only for the top technical profile. Many companies today look for this new role, the role of the business translator. The business translator is a role that is an intermediate step between the business and the technical level that is able to talk both languages. We need that to transform business requirements into data-driven strategies. Otherwise, we will always have a gap between what could be beneficial, what could be valuable for the company or for your stakeholder, and what you build with your analysis. And if the two things are not aligned, they're not generating value, okay? That's the point. This role needs appropriate tools that are not just machine learning techniques. Tools like this, okay? Business people talk with, templates and tables and whatever. For instance, this one is a technique called the goal poster. That is a technique that maps business models, business problems, business needs to technical solutions. You need to have a seamless path, otherwise you will create a misalignment from who is the user, where I'm going to use the model, when and how, what are the questions I want to solve, and then from there, I will start sketching the business metrics responding to the questions, and then from the business level, I will map them to the technical level. Otherwise, the mismatch is guaranteed, be assured. So this flow is the flow that guarantees that the previous picture I showed, the one on decision-making with the different strategies of analysis, can be actually valid, okay? I'm stressing this because, again, as technical players, we usually play basically in this field, okay? Okay, what is the technical question and what quality metrics can we achieve at what level? But the big picture is much bigger than what we do in our localized studies. So I think the take-home message here, I think, is whenever you start the process of data analysis, web analysis, whatever, always start wondering, who am I creating value for? And what are the actual questions that will make life of someone else easier? Otherwise, it's only my life getting easier. Okay? Thank you. Any questions?
Yeah. Is that working?
Want to use this?
Okay. Okay. Well, very interesting and how to say, very ambitious direction. Let me say in this talk. You covered a lot of things here.
Yeah.
Yeah, you were talking about quality data integration, multi-perspective. Yeah, business also model, and I was wondering about a lot of things, but maybe let us start about maybe questions about the audience, then I will allow myself from some of them. Audience, maybe online questions as well?
Yeah, I see some chat, but
No, it's not so far. Maybe people are still shy. Marco, we have another mic.
Thank you. Thank you for your introduction. And you talked about a certain point about the quality of the results, okay, and with respect to their explainability. I would like to know if you have experienced some approaches or models which are going to take into account the issue and how you started thinking about it and how
Yeah. So clearly, explainability is a very popular issue addressed today by many researchers. In our lab, we cover explainability from two perspectives. One is explainability of deep learning models. For instance, in detection of objects in imaging. At the moment, we have a mixed crowdsourcing plus data-driven approach, where basically we have we are actually in the process of creating games, basically gamification approaches over the internal behavior and results of a deep neural network. For instance, we try to extract activation maps in the middle layers of a neural network. We pull out and try to, we actually run clustering, whatever, to detect the most relevant features. And we ask people to tell us what are these features. And we try to see if we perceive an actual description of the various steps that lead to the final decision. This is an example, for instance. Okay.
So the human in the loop says something.
Yes. In this case, it's a human in the loop approach with crowdsourcing gamification in the play. Yeah. Okay.
Thank you, Marco, for thank you, Marco, for this presentation. My question is also under the umbrella of quality. I think that a lot of us we try to put just maybe the trust behind the word quality. But I think that we have a lot of things like, the fiability or how we can really evaluate the quality. If we manage that with the business aspect, I think that we do not have a lot of information about the quality and how we can evaluate it. Mainly if you have some resources that are coming from enterprises, and as you know, we do not have a lot of information. So how you can manage that?
Yeah, okay, thank you. That's a very crucial point. So I think we have two levels here. So I guess you are mainly thinking about quality of the data, right? Not quality of the process or the analysis. Okay, so for data quality, clearly, as I said, companies themselves don't trust their own data. So just imagine how should we trust theirs. But the main concern so while, for instance, we run a lot of social media analytics and whatever, we end up with the results and we never really wonder deeply inside, is this descriptive of actual happenings in the world? But this is, if you take the business perspective, this is typically the first question they ask. Yeah, you're telling me about social media, but is it really something that describes my business? And most of the time, the answer is, who knows? I don't know. Okay. We don't. So in this sense, we don't have. I mean, we have low individual experiences where companies validate the outcome. For instance, we recently ran a work with comparing Italy and the US on a specific, it's very peculiar business that is blood donation for a company that builds some technologies for that. And blood donation, for instance, is a very niche ecosystem. So we didn't know anything about that. We analyzed the digital space, but then the validation came from the company. So afterwards, once you run all the analysis, you collect the data, then you talk to the company and basically they were the ones saying, yeah, this makes sense, this does. And this is in line with, I think, what I said before, don't expect surprises. First thing is, just be happy if you have quantitative measures of things that you are actually not knowledgeable about. So validation from the business side to us is usually the best thing we can get.
Well, we have a problem with the mics.
You want to do this?
Yeah,
sure.
First.
Yeah,
Okay, so you have to wait.
yeah, okay.
Okay, Marco, thank you very much for the talk. It was very time. You like invited talks should be. Yeah, no equations, no algorithms. Yeah. Let me ask you this. It was probably 5-6 slides before the end. You were saying that although we do research on IoT for decades, operationally there are problems. And I was surprised for that. Actually, my daughter at Thessaloniki is working for a cluster of companies which try to sell smart houses. So what is the problem? Interoperability in some sense. Can you please elaborate here?
Yeah, I think that there is a bunch of problems intersecting here. That is, I don't think there are technical issues, mainly, because the technical part, I'm not saying it's all, but I mean, it's fairly covered. If you look at these products, most of them run on standard platforms, on standard communication protocols. So it's not a problem about the fact that these devices are not able to talk to each other. Because, for instance, so if you look at this, they mostly run on either Wi-Fi or Zigbee or Bluetooth. I mean, they're not really not able to talk to each other. The problem is, I would say it's mostly a business problem. Companies tend to build their own silos.
Well, standards probably.
They build silos, commercial silos, I would say, so that they keep control on the entire stack of the value, from the device they sell, but not only there, to the data it produces, to the communication, to the app, to the analytics. Why? Because that's the way they keep the value of the analytics, and they sell from the device to the app, to the subscription plan. Clearly, there are solutions that try to integrate that. For instance, some of the Tuya and others, or Smart Lights, are apps that are sort of integrators of multiple providers and so on. And it's working because the digital level, the technical level works. But the producers tend to keep things separate. And I mean, I don't know about the finance ecosystem, but for instance, the same happens for if you have electric cars, right? In Italy, there are, I would say, 20 providers of places where you can plug in your car for charging. Basically, you need either one app for each provider, or these integration apps that, again, do not integrate all the providers. So anyway, you need to have 10 different apps installed on your phone to charge your car. And
you don't have 10 cars.
But you have one car. That's the problem. And you hope every time that next plug-in station will work with the apps you have. And the same is for home automation, I would say. Either you stick to a single ecosystem, or if you go out, you need to have this problem. Yeah.
Other questions? Yeah.
Thank you for a very interesting. I agree with you for that it's important to consider the business value when starting research project. I'm a researcher in a university, so based on my experience, research that we usually has deeper contact with the real business. So, do you have any suggestion for researchers that we need to develop this kind of mental strategy to get to know how to What is the real business model in this kind of research?
Yes, no, I mean, I share your position because in a way we run some industrial projects, but we are mostly research, theoretical research. So I think that the only way to really grasp this concept of value is to talk with stakeholders. Because you realize that because until you only think about your own perspective, or you talk to your own people or university people, that's the research. And that's oriented to the technical work, improving models, improving performance in terms of accuracy. With those talking this company, this, you know what? Today we don't even hire data scientists anymore. With a very, very high skills into data science, because now we have so good models that you can mostly take them off the shelves and run them. And honestly, we don't care if it's 92% accuracy instead of 94%. Who cares? Our main problem is to match with our business need. Okay, so this is really bigger for the ones to improve.
So it is productivity, you mean, or
Yeah, no.
by using tools you can
By using tools, you don't need extremely high technical skills or large data science lab, because today you run a library, you use BERT or whatever the models, and somehow they work. And the other point is the company sometimes, most of the time, don't perceive a 2% improvement in performance. The important is that the 92% matches their problem. And it's much more risky, that part. That you improve 2%, but you don't respond to the question. Then understand it's going to be even down 2%, not respond to the question, and they have 90% correct answer. So I would take this first. Talk to people that
Can I ask you some questions? You mentioned something about the business translator that maybe the society will need to cope with. So, are you designing any methodology to help people to I don't know, to make this happen, and then any measures or indicators to do that?
Yeah, in a way. So so in this sense, I wouldn't say it's a research problem. It's more like an education problem.
Yeah, that's what I'm looking at. Methodology.
Yeah. So for instance, today many companies ask for courses for this kind of reskilling or upskilling of their people that need to move from traditional managers to data-driven managers, let me say. People that need to be able to understand the language of data science, whatever, and still be managers. This is what they ask for. And for instance, the example I showed you here, this goal poster is one of those methodologies. I mean, to us, it may seem obvious that we need to go from the goal to the user, to the use case, to the question, to the action. But a manager finds this flow something new. And the bridge between, so the manager in this picture would stop at the business manager, the business question. The technicians would work on the right side, the technical questions. The methodology is this whole high-level picture that lets you bridge the gap. So the methodologies are not, again, not formulas, not mathematics. It's more like a managerial methodologies, I would say, similar to this. This is one of those methodologies we teach to companies. It's very basic to us, but that's what they ask for, and that's where they transfer the value between the two.
Okay. I don't think that we have questions from the audience. No. So again, I would like to thank on behalf of all of us, Marco, for his nice and excellent talk. Let's give it a big shot. And then maybe we can have just, if you want to have a small break, 2 minutes to prepare the slides with our next session, which is related to the tutorial with Professor Manolis, Koubarakis, and Dimitri Bibilas from the University of Athens in Greece. So you can stay or you can just walk a few minutes just to prepare the slide. Thank you. And then also you can use the coffee makers if you want to share it. Yeah, okay. Yeah. Okay. Yeah.
Yes.
Ahmet, access the floor. Now you can hear your next one. Here you are. Okay. Do you need any pointer? Okay. So you can have one here or you can use yours. Hi, how are you? Good. I didn't see you doing.
Το πρωί ήσουν εξαφανισμένος. Καλά, εσύ πώς πας. Τι έπαθες, κρύα χέρια έχεις. Τι έχεις παιδί μου. Τρέπεται, φοβάται, τι κάνει.
So and you can move for the slides. I don't know if it works with video.
Στην ταχύτητα μας.
Πώς λόγω.
Με τον...
Μόλις κάτι
Όλοι, η παλικάρια έτσι.
Great.
Richard the Great. There is a problem to any solution.
And maybe this will work for you. Do it like this, and then the point. Yeah.
See, it's like.
You want to go?
Water?
Water, beer.
You have now? No.
It's game already. It's down into the okay, guys. We'll start. Okay.
Yeah. See, this is online.
Okay, so now we're gonna start our tutorial titled Data Modeling and Query Answering for Linked Geospatial Data by Professor Manolis, Koubarakis, and Dimitris Brambilla, both of them from University of Athens in Greece. Do I read your long paper? Okay. Let me say some words about you, Professor. Okay. Professor Manolis is the director of graduate studies in the Department of Informatics and Telecommunications, National and Kapodistria University of Athens. He leads the artificial intelligence team. He holds a PhD in computer science for the National Technical University of Athens and MS Master in Computer Science from the University of Toronto and a diploma in mathematics from the University of Crete. He is a fellow of Artificial Intelligence, European Association for Artificial Intelligence since 2015, and president of Hellenic Association for Artificial Intelligence. He is a member of advisory board that implements a Hellenic national strategy for artificial intelligence. His publication record is more than impressive, with more than 7,500 citations and an H-index of 45, according to Google Scholar. Good. Well, his research has been financially supported with a total amount exceeding millions of euros by the European Commission, Hellenic Foundation for Research and Innovation, the Greek General Secretariat for Research and Technology, and so on and so forth. He currently participates in the European project AI4 Copernicus. I spell well. As technical manager of the project, which brings data to the platform used for the project, and he leads the work on semantic data cubes. I hope that I did it well. Probably you will do better than me. I'm really so glad to have you and introduce you, Professor Manolis. You have the floor. Maybe some words about Dimitri. He will maybe present some part of the tutorial. Dimitri is the postdoctoral research at the Management of Data, Information and Knowledge Group with the Department of Informatics and Telecommunication, National and Kapodistri University of Athens as well. He was under the pure supervision as a director of the thesis, and in the area of query languages for the semantic web and distributed data process. Maybe I'm going to stop here. Thank you again for sharing with us your expertise. And I'm looking forward.
Thank you, Richard, and thanks to all the chairs for inviting us to give this tutorial. I'm especially thankful to Dimitris, who agreed to join me. Dimitris has done his PhD with me, but unfortunately, he will soon be going to industry and he will leave us. So I'm very sad about this. But this is what happens when people grow up and they want to become independent, and this is life, I suppose. But today he is with me here, and I'm very happy for this. So our tutorial is data modeling and query answering for linked geospatial data. And actually, my interest in geospatial data started even since when I was a master's student at the University of Toronto. But it became more substantial when we had a common project with Yannis called Koubarakis, where we studied geospatial but also temporal data. And I was telling Yannis this morning that we actually wrote a book at the end of the project. And I wrote the concluding chapter of the book. And when we started this work, I went back to this book out of curiosity. And what I found in this chapter was a suggestion that we wanted to study these problems, which is really fine. I mean, in the sense that somehow we thought about it in the past and finally we did it, right? So we started this work in around 2010. And today we will present you only some results of the many results that we have obtained since that time. So I will do some introduction and motivation of the problem. Dimitris then will do part one, which is about modeling and querying. He will also present some linked data stores for geospatial data. Then I suppose we will have a coffee break. Sure. And then we will continue with part two, where I will talk about geospatial knowledge graphs and question answering in knowledge graphs. Question answering is, of course, a different thing because the question is the natural language, not as in part one, where Dimitris will assume that the query, the question, whatever you want to call it, is in a query language. Okay, and then I will close the session for basically proposing some open topics where people can do research in this area. Okay, So why this topic is interesting? Because geospatial data is everywhere these days, right? I mean, you can't really imagine, we can't really imagine how the world was before we had, our mobile phones and these maps that allow us to go everywhere, right? We wanted to come here to Biarritz and we go to Google Maps, type Biarritz, and we immediately see, look, nice. This nice view that we saw today, the exception, yeah. Google Maps, of course, is a commercial product, but we can also go to open products like OpenStreetMaps to see the same kind of information. Another category of open geospatial data with which we have worked a lot is Earth observation data from satellites. So we had a lot of projects in the context of the Copernicus program of the European Commission, and a lot of our activity has been motivated by this. Today, we will not spend time discussing satellite data, although we could. We will basically move a level up and talk about geospatial data, but of course, satellite data is also geospatial. I would like to start by giving an example of a data set that Dimitris will use later in his presentation, which actually comes from satellite data. The Copernicus program of the European Union has a service called the Land Monitoring Service, and this service produces every now and then a product called Corinne Land Cover that basically gives the land cover of various areas of 39 countries in the case of the 2012 version of the dataset of the European Union. So basically there is a hierarchy of land cover, which you can understand as an ontology, and you have classes like vineyards, for example, or olive trees, or the kinds of coverage that you might expect, yeah? And you have a proper mapping unit, and these data files are made available as raster or vector GeoD for various geodatabase formats. Now, in our case, we have decided to use linked data technologies for making datasets like Corinne Land Cover available. And you will see Dimitris later on talking about these technologies in more detail. But from a high-level point of view, the reason that we decided to adopt these technologies and push for their extension with geospatial data functionalities is because linked data allows us to open data from various data silos. So, for example, in the case of Earth observation, a lot of satellite data is essentially in the archive, but our view is that they should come out and be made available on the web so people can find them and use them. And not only Earth observation experts, but also experts that are not, but also users that are not experts in Earth observation. In our case, they have to know semantic technologies. I mean, this is the technologies that we evangelize. This is the technologies that we use. These are the technologies that we will present today. And a lot of the value of this data comes when we interlink this data with other data that is on the web. For example, the Corinne Land Cover dataset that I presented earlier, you can interlink, for example, with global administrative areas. So you can see for an area of cover, you can see in which administrative area you go, right? Or the opposite way, an administrative area, what kind of land cover it has, okay? Similarly, you can find information about cities that, like Biarritz, for example, that you find an entry in Wikipedia. The linked data equivalent of Wikipedia is DBpedia. Then from DBpedia, you can have a link to the land cover of that area, right? And see from a geographical point of view what kinds of things you will see around Biarritz. So there are some interesting things that the linked data paradigm offers you. And today we are assuming this paradigm, and we will tell you more about how to query data in this paradigm, how to build knowledge graphs in this paradigm, how to ask questions over knowledge graphs in this paradigm. What is important to notice here is that we are not just some, typical academics that have adopted linked data and now they study linked data, they write papers on them, and they have some good friends who invited them to give a tutorial about the same thing, right? What I would like to stress is that linked data is today used, at least in Europe, by cartographic agencies. Actually, the first cartographic agency to use them was Ordnance Survey in the UK. Although for some reason they don't seem to be so excited about linked data lately, from what I can see on their website. But the cadastre in the Netherlands has a lot of services and a lot of data sets offered as linked data. And the most recent champion of this technology is the cadastre service of Switzerland. So I give you here some links where you can check out what these cartographic agencies offer with respect to linked data. Now, in our work, where we study satellite data, we have developed a whole pipeline that starts with the satellite data that arrive in the ground segment of the satellite and ends up with an application. And we present you this pipeline here. We have all the tools for the green boxes that you see in of the pipeline. But today, we will only concentrate on storage, querying, and question answering. This box, this box down here. Okay, so we don't need to see the others, but if you want to look at these papers of ours, you can read more about this. And before I give the floor to Dimitris, I would like to tell you that the work that we did with these linked data sources has actually resulted in at least one case in an operational system. So in the National Observatory of Athens, there is a service called Fire Hub, which is used during the summer seasons, mainly when we have wildfires in Greece, to monitor the fires, okay? So this polygon here basically means that this area there is a fire in this area, and then you can look, you can use the system to see how the fire evolves. You can use the system to look at historical information. So it's really an operational system, and it has been built using the kinds of technologies that you will hear about today. So I give the floor now to Dimitris to continue with models and query languages for linked geospatial data.
Okay, so this part of the presentation is about how we can represent spatial information into the semantic web and make it available as knowledge graphs. So first of all, a couple of words regarding the background for this section. This comes from GIS systems, first of all, geographic information systems like ArcGIS or QGIS. And then regarding research results, this comes from spatial database research and also from spatial logics and reasoning. And finally, we use a lot of things from industry standards and implemented systems For example, from geospatial databases like PostGIS, Oracle Spatial and Graph, SQLite, and other systems. So first of all, we will talk about the data model STRDF and the query language STSparkle. Then we will see the Open Geospatial Consortium standard GeoSparkle. Then the framework RDF5 for dealing with incomplete geospatial, in general, incomplete information in RDF. Then the language GeoSparkle class for also incorporating information about raster datasets. And finally, the proposed language GeoSparkle 1.1, which is in the draft version, which is the next version of GeoSparkle. So the model STRDF, the purpose of this model is to be able to represent geospatial information in RDF graphs. So it is an extension of RDF that has a geospatial dimension. Specifically, it has two spatial data types in order to deal with geometries. And the geospatial information is represented using spatial literals of these data types. This information can be expressed using the Open Geospatial Consortium standards well-known text in GML for the serialization of the geometries. And also, the STRDF model has a temporal dimension that will be not covered here in this tutorial. So, as an example, we have a specific domain where we want to represent and create information regarding administrative areas of a specific country, for example, of Greece. So what we want to do is, first of all, create a domain ontology that contains specific classes and hierarchy of classes regarding our use case. For example, here we have a hierarchy of administrative types. And we have also two properties, the subclass property and the belongs to property. So all administrative types are declared to be subclasses of administrative unit, whereas the belongs to property is used to declare information that a specific region, for example, belongs to a decentralized administration, etc. So after we have a domain ontology, we want to link this domain ontology with an upper level ontology or a top level geospatial ontology. So this is an ontology that is used to represent more general information regarding spatial objects. So in our example, we have three classes: the spatial object, the feature, and the geometry. And we also have some properties. For example, we say that a spatial feature has a specific geometry and is connected with this class with the property has geometry. Okay, so then we want to link our domain ontology with the upper level ontology, and this happens with a subclass property between administrative unit and the feature class of the top level of geospatial ontology. So here we have an example of some RDF triples. So the first triples are standard RDF triples. They do not contain geospatial information. For example, we have a resource called Olympia. We say that it's of type municipal community. It has a specific name, which is a string, and it has a specific population, which is an integer. And then we have a fourth triple that contains geospatial information. So we use the STRDF property has geometry to denote that the resource Olympia has a specific multi-polygon as a geometry, and it's serialized using the well-known text serialization formats for geometries. And also we declare the coordinate reference system, which is the way that we plot the geometries from the three-dimensional sphere that is the Earth to the two-dimensional space. So there are different systems with different precision regarding different areas of Earth. Now, after we have represented this kind of information into RDF, this geospatial information, We also need a query language, so we can obtain information from the geospatial RDF graphs. So with the data model STRDF, we have the STSparkle query language. Okay, this stopped working. So it's an extension of Sparkle 1.1, which is the standard query language for RDF graphs. It offers a family of functions for querying geometries, and the functions are taken mostly from the OpenGIS Social Consortium standard OpenGIS Simple Feature Access. And they are similar to functions and that can be found in the geospatial relational database systems. For example, PostGIS. So as an example of STSparkle, you have this query here that computes the parts of burnt areas that lie within coniferous forests. So the basic fragment of Sparkle are the triple patterns here that match specific triple patterns to specific triples on the graph. So we want the burnt areas that are of a specific type of the burnt area, and also we want the geometries of these burnt areas that we take in the variable PA geom. Then we also need forests, which are regions that have a specific land cover, coniferous forests, and we also take the geometries of forests in this variable FGeom. And then we perform spatial operations on these two kinds of geometries, on the burnt area geometry and the forest geometry. So for this, we use a filter clause in STSparkle that takes as argument a geospatial function that returns only the geometries that intersect with each other. So only burnt area geometries and forest geometries that intersect. And then we also have some spatial functions on the select clause of the query. So here the union function is a spatial aggregate function that takes a set of geometries and returns their union. So the area that all of these geometries occupy. And this aggregate function operates grouped by burnt area and burnt area geometry. So for each burnt area geometry, we union all the forest geometries that intersect with this geometry and return the final result. So this happens because a specific burnt area may intersect with more than one coniferous forests. Thank you. So apart from STRDF and STSparkle, we also have the OGC standard GeoSparkle that was published in 2012. And this contains several modules. First of all, we have a core module. And then we have the topology vocabulary extension that offers a relation family regarding spatial relations between features. We have the geometry extension that offers serialization of geometries like serialization in well-known text of GML. The geometry topology extension uses the geometry extension in order to define relations that operate on geometries. So we can have a function that operates on specific geometries and find the geometries that intersect or lie within each other, etc. Finally, we have the RDFS entailment extension that used in order to entail knowledge that is not explicitly stated in the RDF graph. And finally, the query write extension. So if we want to compare GeoSparkle with STSparkle, you can roughly say that STSparkle corresponds to these two modules of GeoSparkle, the geometry extension, geometry topology extension. But again, this only is the SSparkle because it omits the temporal dimension. So SSparkle also has a temporal dimension, as we said, but GeoSparkle does not deal with time at all. So here is an example of the topology vocabulary extension. So again, we have some triples. We say that Olympia is of type municipal community. We say that Olympia municipality is of type municipality, and we say that Western Greece is of type region. And also we use the relations from the topology vocabulary extension to denote that Olympia is within the Olympia municipality, and the Olympia municipality is within the Western Greece region. So a query that someone can ask is find the region in which ancient Libya is located in. So the answer should be Western Greece by transitivity of the within function, but this is not supported by geosparkling. Now, regarding the query rewrite extension, this enables translation of qualitative topological information that appears in a query to quantitative. This is done by rewriting the queries with triple patterns involving topological relation into queries with topological functions of geometries. And the rewriting is based on RIF rules. So instead of having to perform, for example, some computation with geometries, we can use directly the qualitative topological information. Now we have here another example, which acts as a motivation for the RDFI language that deals with incomplete information. So we have the triples that the resource region A has a specific geometry, polygon A, in a specific serialization. So we have a specific polygon for region A. We also have a specific polygon for region B. But then we have another resource, region X, for which we don't have the exact geometry. So we don't have a specific polygon or specific point for this resource. But we know that it is within the region B. So can we answer this query that asks if region X is contained in region A? Again, the answer should be yes, as you can see in this slide. But this is not supported by geosparkling. So regarding RDFI, it is an extension of RDF with incomplete information. In order to represent incomplete information, a new kind of literals is introduced, which is called illiterals for its data type of RDF. These literals are about property values that exist in the graph but are unknown or partially known. And the partial knowledge is captured by constraints of an appropriate constraint language L. So in this context, the RDF graphs are extended to RDFI databases, which is a pair of the graph and a phi, where phi is a quantifier-free formula of the language L. So also formal semantics for RDFI and sparkling query evaluation on RDFI graphs are given. And this is about, we take into consideration two different representation systems. The first one is construct queries without blank nodes in RDF templates, and also only deal with monotone graph patterns, that is only the operators end, union, and filter. And the second representation system is about construct queries without blank nodes and with well-designed graph patterns. That is a graph pattern that using only end, filter, and optional, plus some intuitive conditions. Also, the computational complexity of query evaluation under these settings has been studied. And the query answering is co-NP complete in terms of data complexity for certainty queries and various interesting classes of spatial constraints. This is in contrast to the log space complexity for the standard sparkling. Now, the language geosparkle plus is an extension of geosparkle in order to integrate raster data into the semantic web. So what we have said so far deals with vector geometries, where we have the representation of a geometry using, for example, polygons on lines and your points on a coordinate reference system. Whereas in the raster data, we have a specific grid, which is divided in different cells, and each cell contains a specific value that corresponds to some information that can come, for example, from satellite observations, etc. So, geosparkle plus contains new filter functions based on the raster algebra operation, for example, raster plus or raster smaller, in order to modify the values of the raster cells. And also, geosparkle plus allows to perform combined vector and raster data analysis from the same query. GeoSparkle Plus, first of all, contains an ontology that extends the GeoSparkle ontology. So on this slide, in this part of the slide here, we have the GeoSparkle ontology that contains the class for feature and spatial object. And then we have the GeoSparkle Plus ontology that it is linked to the GeoSparkle ontology. It contains classes regarding coverage and rasters. So it contains a class hierarchy. So finally, raster is a subclass of all other classes. And as a result, it's also a subclass of the spatial object class of GeoSparkle. Again, this can be thought of as the top level ontologies. And then again, we have a domain ontology. For example, here we have an ontology about a specific use case that it is about floods. In an event of flooding of some area. So we have a specific raster coverage here, which is of type raster. It has a specific scale, where the scale is also interlinked with the units of measurement ontology. And it has a specific serialization here as a rasterization literal. So using GeoSparkle Plus, we can answer questions like here, this use case, where we want to find all roads which are not flooded by more than 10 centimeters. So this is useful in the case of a flood event. For example, to find the roads which are passable by a vehicle. So for this use case, there exists a road network vector dataset. So this contains a specific line string that correspond to roads. And we have the flood altitude raster dataset. So this is a raster dataset, for example, it may come from some sensors that give information about the altitude of the water in a specific area. And this is an example of a query that uses these two datasets in order to answer the previous information, to find the roads that are not flooded by more than 10 centimeters of water. So here we have roads with a specific geometry and a specific serialization. So these are the vector geometries. We have a flood area which has as coverage, as a grid coverage, a raster. And this raster has a specific serialization using the JSON format. And here we use some functions defined in GeoSparkle Plus, specifically the raster smaller function that only returns cells of the raster serialization that are smaller than 10, so the value is less than 10. And finally, we have a geospatial intersection between the well-known vector geometries and the result of the first of this filter here. So this intersect function is an extension of the simple GeoSparkle intersect function that operates only on vector geometries because it operates on vector and raster geometries at once. Now we have also the next version of GeoSparkle standard, which is called GeoSparkle 1.1. And this is currently, as we said, in a draft version. And the work on GeoSparkle 1.1 started in 2019 by OGC, which reactivated the relevant working group. And so since the publication of the first version of GeoSparkle in 2012, GeoSparkle has been widely used by a lot of systems and in a lot of use cases. So from this heavy usage, there were a lot of requests for extensions and incorporation of other functionality. So GeoSparkle 1.1 will contain non-breaking changes with respect to the first version, and the working group foresees another future version that will no longer be compatible with the 2012 version. So there is a living document with the changes in the draft of GeoSparkle 1.1 of found in this URL. So regarding what more than the first version of GeoSparkle, the new version will contain, first of all, it will contain an extended ontology, where it will also have some classes regarding collections. So, for example, you have a spatial object collection, feature collection, and geometry collection for representing collection of spatial object features and geometries, respectively. And this comes from this motivation came from similar functionality that popular GIS tools contain in order to export collections of data sets. Furthermore, it will contain new spatial object properties that define scalar properties. For example, the length of a line string, the area of a polygon, the volume of a three-dimensional structure, etc. This come in metric version and simple version. Where in simple version, you have to define the unit of measurements also. Also, it will contain some feature properties like the bounding box of the ontology or the centroid of the bounding box of a geometry or the centroid of a polygon, for example. And it will also contain new serialization formats. So in GeoSpark 1.1, there will be support for GeoJSON, KML, and DDGS, and also new functions that will transform between these formats. Also, it will contain non-topological query function with add functionality to the already existing ones. And these are functions that similar functions existed in geospatial database, for example, but were missing from the first version of GeoSparky. For example, a function to compute the area, the coordinate dimension, to take, for example, the nth geometry from a geometry collection, to denote if the geometry is simple or it is a composite geometry, etc. Finally, it will contain a more spatial aggregate function that accept as input a set of geometries. So, for example, we can have the aggregate bounding box, the aggregate bounding circle, the aggregate centroid, the aggregate concave hull, and the aggregate union of a set of geometries. Finally, GeoSpark 1.1 will contain a profile definition that will use the RDF profile vocabulary that facilitates formal definition of specifications. And also it will come with an RDF validation file. This is a SACL file in a shapes-constrained language, which is used to make sure that specific conditions are present in a specific RDF graph. For example, using this file, you can automatically ensure that each entity in the RDF graph that corresponds to geometry has at least one declared serialization, or that an entity cannot act as both subject and objects in triples with properties, has geometry or is a property of it. So this was a section about data modeling query language for geospatial information RDF. So if there are no questions, we can continue. Yes.
I wanted to context here. So I understand the vector data, raster data, and there are rules operators. There is post BIS limits of all of this, and you can type in queries to get data. Right? So with regards to your tutorial on Sparkle, GeoSparkle, from which aspect is it coming? Is it a different kind of data set or different kind of query language?
Well, it's a different data model, essentially. So we represent all this information as knowledge graphs. And having done so, we can facilitate things like either linking with other data sets that you saw also in the introduction of this tutorial. And also we can develop applications such as question answering applications that you will see later that use this knowledge graph and use techniques that are tailored for knowledge graph in order to perform question answering from natural language questions, something that is difficult if you have data relational database, for example. So the whole motivation comes from the fact that representing this information knowledge graph, you can have a lot of other things that can be implemented on top of that.
Are there tools can help me write GeoSparkle queries? So does PostGIS support GeoSparkle?
No, actually, if you want to when you come to the world of knowledge graphs, you can use systems that store and query knowledge graphs that we will see next in the presentation. So some relational databases like Oracle has a version which is called the Oracle Spatial Graph that supports, for example, RDF and GeoSparky. But in general, when you use a relational system, you cannot don't have the option to pose GeoSparky or Sparky query. So you need other systems.
Do you use our one or our two to represent your data? Or do you use our two or each?
Actually, most of the accessibility needed for the ontology of GeoSparky is already present in RDFS. So
you operate on RDF as well?
Yes, we use mainly subclass hierarchies and properties hierarchies. So they are already present in RDFS, so we don't have our axioms.
Okay. And how about reasoning with the RCCA that changes for space? Do you support any of that?
No, this is about the query write extension of GeoSparky can be maybe used as RF rules. But in the system that we will see that we have implemented as a group, we don't support reasoning with respect to spatial reasoning with respect to RCA, for example.
So
No.
I can answer I can answer in a more complete way. So in the RDFI model, Dimitri, maybe you can go back to the RDFI model. Go to the example. Stop. So in the RDFI model, actually we do. Because this is, I mean, the within is from not RDFI, but from the dimensionally extended the sexual model, right? So it's essentially the same thing. So we have a couple of papers in this area, but we don't have a system support. So that's exactly what we say. For the usual reasons, I mean, the complexity of this then becomes unmanaged for processing. So I think we should have built the system anyways, but we have.
Okay, so now we're coming to the section of tutorial regarding geospatial RDF stores, as we said. So there are several systems, research prototypes, and also commercial systems that support spatial information in RDF. Some of them support supported partially, or in modeling and formats that are only used by the system, and others support languages like the one that we saw, Spark and GeoSparky. So regarding the first prototype, it comes from a publication that it supports a specific language called SparkQL ST, which is a language defined in the publication. And it supports DML serialization geometries, spatial and temporal variables, and spatial and temporal filters in RC8 model and Allen relations. And it also uses NAR3 as a spatial link. So next we have another system that extends a well-known RDF store, RDF3X, with GeoSparky support, where the geometries are represented by as typed well-known text literals, and only a specific coordinate reference system is supported. And also, it also uses NAR3. So next we have a commercial system called Parliament. That it was the first GeoSparky implementation. supports several modules of GeoSparkle. And as a backend, it uses Berkeley DB and also Gina ARQ. Gina is an RDF library as Sparkle processor. It uses standard R3 for indexing the geometries, and it is open source. Next, we have Strabon, which is a tool developed by our group at the University of Athens. So Strabon builds on top of an RDF library called Sesame, and it uses as a backend a general DB interface that can be specialized in a specific RDBMS, for example, PostGIS, MonetDB, etc. So Strabon supports both STRDF, Sparkle, and GeoSparkle. From GeoSparkle, it supports these three modules. It's a system that supports multiple coordinate reference systems, so you can store and query datasets in different CRSs. As we said, it's built on Sesame RDBMS Sail library, and it uses GeoSparkle relational database at the backend. And the default backend is PostGIS, and in this backend we have an R3 over gist index. Also, Strabon has, as it supports STRDF and Sparkle, some temporal features that translate temporal triples to standard RDF triples using named graph. And again, it relies on a temporal extension of Postgres as a backend. Next, we have UCChem from Open Sahara, which is a spatial plugin for Sesame by Open Sahara. It supports several modules of GeoSparkle, but only the specific coordinate reference system. And it has several available spatial indexes like R3 over GIST, Quad3, GeoHash. And it is open source. Another commercial system is Allegro Graph, which is a quad store. It doesn't support GeoSparkle, it only supports point geometries. And only supports a few spatial operations like buffer bounding, box distance. But it includes temporal functionalities like date times, time points, time intervals, etc. And also there is a version with federation in order to run in multiple machines. Another system is OpenLink Virtuoso. This in a stable version does not support GeoSparkle, but there is some support for GeoSparkle in the development branch. It deals only with points. The spatial operation that it supports is a subset of the SQL standard. It supports multiple coordinate reference systems. It uses well-known text for serialization of geometries and R3 for the spatial index. So Blaze Graph DB, it also uses Sesame, no GeoSparkle support yet. It has a specific defined typed literals, which come on the form of latitude, longitude, and longitude time, in order to also deal with the temporal dimension. It supports rectangular distance queries over geospatial coordinates, possibly combined with range scans over the temporal coordinates. So it uses combined query function over spatial and temporal filters. And also it uses a generic Z-order index implementation for dimensional range scans. So in order to ensure that during the fragmentation of multidimensional spaces, areas close to each other are also stored close to each other to be more efficient in query evaluation. Next, we have GraphDB, which is a popular RDF triple store. It supports many modules of GeoSparkle and also supports multiple coordinate reference systems. In order to activate the GeoSparkle support in GraphDB, you have to use a specific plugin, which is called GeoSparkle plugin. And this plugin contains indexing algorithms based on Lucene Spatial, Quad or GeoHash prefix tree. Also, it has an option to operate on approximate mapping of geometries using a precision parameter that the user can define. So this way you can perform geometric operation more efficiently if you can afford to have to lose some precision and not always have the correct results. Also, another feature of GraphDB is that you can reconfigure the algorithm, the indexing algorithm and the precision through Sparkle update statements. So you do not have to stop the server and reconfigure and restart. If the user has is able to perform update statements, he can also reconfigure these parameters. And also it contains an option for rebuilding the GeoSparkle index on demand. It supports, again, this the specific coordinate reference system. And also it has two fast bulk importers for dealing with large data sets. Stardog is another RDF triple store that contains partial GeoSparkle support. For well-known text serialization, it has the points and rectangles by default. And you can have more complex geometries if you install the Java topology suite. It supports specific functions, and the spatial indexing is based on Lucene Spatial or GeoHash prefix tree with a specific accuracy. Also, it supports approximate mapping as GraphDB, controlled with a precision parameter. But this time, the precision must be specified on database creation. Now, RDF4J is an RDF library for managing RDF data written in Java. And this also supports GeoSparkle. So RDF4J has different types of storage. It has memory storage and native storage in disk, and also it has the Lucene Sail and these derivatives for storing data. So by default, GeoSparkle is supported in any type of storage. The Lucene Sail and its derivatives have built-in optimizations for GeoSparkle querying. So if you use the Lucene Sail, you can have more, you can achieve better performance. RDF4J spatial indexes by default all geometries that are about that act as objects in the property as well-known text. So all geometries that are present in the RDF dataset that belong to this property are by default indexed. And also, if you use the Lucene Sail storage, you can perform several configurations for customizations for the indexing. So Apache Gina is another library that supports GeoSparkle. It supports the specific module of GeoSparkle, and all indexing and casting is performed during query execution. It uses three indexes: geometry literal, geometry transform, and query write, and supports the specific coordinate reference system. And as we said, we also have Oracle Spatial and Graph developed by Oracle. Again, it supports the core module, the topology vocabulary extension of GeoSparkle, the geometry extension, the geometry topology extension, and the RDFS intelligent extension. It has support for different CRSs and uses an R3 for multidimensional indexing. And also, in Oracle Spatial and Graph, you have the option to express and query virtual RDF graphs. So you have information that is not native in RDF format, but it can be in relational tables, and you can expose this information in these tables as virtual RDF graphs. Finally, this is a more recent system developed by our group in the University of Athens. So this is a distributed geospark distributed system that it's able to perform geosparkle query processing. It's called Strabo 2, and it is relies on Apache Spark for distributed geosparkle processing. It extends the system that is called query on top spatial for query translation from geosparkle to the Spark SQL dialect. And it also uses geospatial library on top of Apache Spark, which is called Apache Centona, in order to transform the spatial function of geosparkle into a spatial user-defined function in Spark SQL. It uses specific partitioning of the RDF dataset into the cluster, and it supports the simple feature family of geosparkle and in the well-known text serialization. And it's open source that can be found in this repository. So, is there any question regarding the systems part of the presentation? If not,
Dimitri, maybe what you can say as a summary is what are the most, how can I put it? The most comprehensive system. I mean, if somebody from the audience would like today to try one of these systems, because we presented many, which ones?
Well, according to actually this benchmark that we'll discuss in this part of the presentation, I would say the most complete and the most efficient are GraphDB and Strabon. So these are the two that.
So GraphDB by Undotext and Strabon that has been built by us.
So regarding benchmarking all these systems, our group again has developed a benchmark which is called Geographica. It has two versions, Geographica 1 and Geographica 2. So the purpose of Geographica is, of course, to evaluate RDF stores that support geosparkle and STSparkle. It contains two workloads: a real world workload and a synthetic workload. The real world workload has micro and macro benchmark. So when we say micro benchmarks, we mean that we examine specific queries that deal with a specific spatial operator or a specific filter function, whereas macro benchmark are benchmarks that deal with a specific task. So they do not deal with the specific spatial operator, for example. It contains several data sets, the global administrative areas, coordinate cover, OpenStreetMap, GeoNames, Wikipedia, a hotspot dataset regarding fire events, and also have the synthetic dataset. So these scenarios here are about the macro benchmarks. So we have the reverse geocoding, map search and browsing, and rapid mapping for fire monitoring. The systems that have been evaluated are the UCCAN, Parliament, and Strabon, and also some systems with limited functionality, Virtuoso, a system Y, which is one of the systems that we have mentioned, but as we give experimental results, we cannot say quickly the name because of license limitations. So this Virtuoso and system Y have only been evaluated in point-solid geometries. So now regarding the second version of Geographica, here with different color, we can see the additions. So we have another workload, which is a scalability workload. This comes from a combination of OpenStreetMap with Relevant Cover. And the scalability workload has different sizes of, it's the same dataset, but with different sizes. So it goes up to 500 million triples. And then we have a subset of the largest dataset. Now, regarding the scenarios, we also have the geocoding scenario and the computation of statistics. And we also have the scenario of the scalability dataset. We have also evaluated more systems, like, for example, another system, System X, GraphDB, RDF4J, and also regarding limit functionality, we still have these two systems and the 8 variants of the previous systems. So this is the experimental setup. Sorry, I'm thinking about the time. Okay. So I will skip some slides maybe. We have executed for the micro synthetic and scalability benchmark this query 3 times, 1 time in cold caches and then in warm caches. And the query response time goes from submission of the query until complete iteration of the result set. The median response is selected, and the query execution time limit was 1 hour. And for the macro benchmark, it's scenario run as many times as it could in a time limit of 1 hour. So here is a workload dataset matrix where you can see exactly which workload is supported by each dataset, and we also have a workload system matrix where you can see where each system has been tested. So regarding the results of Geographica 2, we have first of all the loading time of the datasets for different datasets, and we can see that for synthetic, the green numbers have the best time achieved by GraphDB, whereas for real world it was achieved by RDF4J. And then regarding the scalability dataset, we again can see the import time, the data loading time. So for the largest dataset, you can see again that GraphDB was more efficient in storing the largest datasets. And whereas RDF4J, it could not load the whole dataset at once, so we needed to chunk it into small fragments. And here you can also see the size of the repository for each system. So here are the detailed results. So we have different types of queries like non-topological construct functions, spatial selection, spatial joins, and aggregate functions. Again, the green numbers for each query are the best result. So we can see that for most of the queries, Strabon achieves the best result, and then GraphDB also achieves the best result for non-topological construct functions. And the other systems also show some timeouts and errors. So now, as we said, the scalability workload has a list of different sizes, up to 500 million triples. And we have tested the scalability workload with Strabon, GraphDB, and RDF4J. Here is some information regarding the dataset. And we also have the number of different geometries for each subset of the dataset, leading up to 500 million triples, where it contains 48 million geometries. So regarding the queries, first of all is a spatial selection that selects as a very large area over Europe. So this is the query. Actually, it asks for all geometries that intersect with a specific, large polygon. And then regarding the other queries, we have a thematic filter based on the code. So we use these specific codes in order to limit the type of results and the number of results that we're taking. So this is the second query of the scalability workload, where it asks for entities that have a specific acceleration of geometry and have a specific type that corresponds to this code. And we also want entities that correspond to a second code, which is between 5,000 and 6,000, with the exception of this number. And what these geometries to intersect. And then we have a third query that it's similar with the second one, but the code, we only want to be one of these specific, the second code, we want to be one of these specific codes. So in this sense, this has fewer results than the previous query, as it has a lower selectivity. So we can see here the result in cold setup and warm gases from 10,000 triples to up to 500 million triples for the first query, the second query, and the third query. And we can see that in all cases, Strabon achieves the better performance, and we can also see the scalability of the three systems tested. So, any question for this part? Okay, so next we have a part regarding geospatial ontology-based data access. So the motivation for this comes from the fact that this image corresponds to the, for example, for the big linked Earth observation data pipeline that we saw earlier. So we have to process the data, extract the useful information, then transform this information into RDF, store it as triples, and perform a geosparkle or sparkle query. So one heavy bottleneck here is the transformation, where we actually have to materialize all the processed, the resulting information into RDF. So in ontology-based data access, yes, also this information is commonly stored in relational databases where we have frequent updates. And for each update, we don't have update triples here. We want to again transform all this information into RDF. So what is OPDA is actually, if we skip this transformation step and we perform a Sparkle query directly on virtual RDF data that are connected to the original data through some mappings. So in order to do that, we define some mappings that say how a virtual RDF triple can be generated from the data that exists in other data sources, like, for example, in a relational database. So there are several systems and also research regarding ontology-based data access. And here we see an example of mappings. So here in the first mapping, we first of all we have a mapping ID, which is this one, and then we have a source query, which is an SQL query. So assume that we have a table in the relational database which is called global administrative geometries, GAG, and we have the query to select the distinct GID, geometry ID, and the geometry itself from the geometries. And then we have the target component of the mapping, which actually says how the virtual triples will be generated from the results of this query. So this query has two columns as results, the geometry ID and the geometry itself. And the target triples take as parameters the geometry ID in order to define the subject of the triple. Then we define the predicate of the triple, and we also take as parameter the geometry. This should be geometry, in order to define the object of the triple. So from information in the relation database, we have triples that define that geometry IDs have as serialization in well-known text the specific geometry. And also we have other mappings. So in the target, in this target component of this mapping, we have more than one triples. So we generate more information here, etc. So from this information, which is stored in the relation database, we have these virtual triples generated. So again, these triples are not materialized; they're not stored, but we access them directly during query execution, and this is possible with query translation. So on top is our PDA system. This is the general architecture of on top. First of all, we have the parser of the query. Then the query is transformed to an intermediate form based on data log. Then we perform rewriting of the query with respect to some axioms in the ontology. And then finally, the result of the writing is translated back, to SQL, and it is sent for execution in the relational database. And the results are represented to the user as RDF terms. So in order to add spatial support to on top, we have modified several of its components. For example, here in the translation, we have a case where we see spatial functions from GeoSpark language, and we translate it to the spatial functions in the underlying PostGIS. And here is an example of a query translation, where we have a Sparky query that asks for variables x1 that have geometry g1, x2 has a geometry t2, such that these two variables, the geometries overlap. So we have the intermediate form in the, which is some data log rules. And finally, we have a query SQL query, which is the result of the translation that uses the ST overlap function of PostGIS between the columns of the geometries in this database table. So another thing that we should mention is that the on-top spatial has been developed by our group in the University of Athens, and it is a fork of the original on-top system. But recently, the on-top system in version 4 also contains GeoSpark support, and it is also available in this URL. So I will very quickly say some things about raster data supporting on top. As on-top spatial works with PostGIS database, we have also implemented what we call a virtual table that accesses. We have imported in PostGIS also raster images. Using this approach, we can also perform a combined raster and vector data analysis from a single query in on-top spatial, but we do not store the raster in a format for raster datasets, as it was the case in GeoSpark Plus and the implementation. So regarding evaluation of on-top spatial, we have used several datasets that are shown here, and several queries with different thematic and spatial selectivities and different spatial functions. So we have used on-top spatial in order to compare it with Strabon and also another commercial system, System O. And on-top spatial is the red one, and we can see that for most experiments it achieves better times. And this happens because from the way that data are stored in relational databases, we can save a lot of joins. Because when we store triples, we have to perform many joins between the different triple tables. But this difference in performance depends heavily on the relational schema and the complexity of geometries. So finally, we also have used on-top spatial with data that exists in external repositories, for example, OpenDAP, which is a repository for Earth observation datasets, using virtual tables in SQL. So we present information of the external repository as a virtual table in SQL database, and we create mappings that access these virtual tables as it is shown here. So this way you can directly fetch data from external data sources and query them using geosparkling. So this was the first part of the tutorial. Any questions? Yes.
Two questions. Thank you. The first one is just regarding slide number 83, I think, with the entire methods. Yeah, here. So just for the module KDD, you have something, a knowledge base behind, and is it frequently updated about the different maybe rules or knowledge in order to indicate how the data are processed or not?
Yes, actually, this is about extracting information from satellite images using, for example, machine learning.
Mm-hmm.
So we have a satellite image, and we perform some analysis. We want to see, for example, the crop type of field, and we perform some machine learning here, and the information and the result of this is, for example, a raster data, a shapefile, spatial information that can be stored in a spatial database. So either we will have a better machine learning method, and we want that has better accuracy, so some results change. So we have updates here, or we also have new satellite images, for example. So all this pipeline occurs again, and new information is added to the database. So again, this has to be again transformed to RDF. So this is why this is a bottleneck.
Yeah. No, because my idea is, of course, this is the path is very normal, but I think that we need maybe more knowledge about if you have some features that you are looking on before processing the data. This is just my question between the module KDD and the processed data.
Actually, you use an ontology that describes the domain during the transformation. Before the transformation, we would not use the ontology, but the ontology that we have created is based on the use case, on what the machine learning methods, for example, extract, the information that they extract. But the same ontology is not taken into consideration for the KDD task. No.
So for us, KDD, there is a data mining. Actually, I don't like this KDD. I would prefer here wider knowledge discovery. Becomes very clear what the case, what it is, and then throw away the last thing. But we had some colleagues in projects that used KDD, and I think my colleague Konstantina, who actually was the first author of these slides, and who actually did get based in this of spatial, chose to write it. So, you know how things sound.
Yeah, okay.
Legacy slides.
Okay, for sure. And my second question is about reusing the queries. Do you think about something, how we can reuse intelligently the query that are already executed before, or not, in order just to add some optimizations?
So, for example, using some caching or something like that on the data level.
Yeah.
We have not implemented something like that in any of our tools for these use cases. But this is something that I think can be added transparently as a module between the storage layer and the query. And then the query must take into consideration what exists there in the cache. Yes, it is something interesting.
There is some work that Theophilus Manolis has been doing recently. Essentially the same kind of problem. Theophilus is another person in our larger. So this is really very interesting. And I think we have a plan to extend it with him geospatial. It's an interesting thing how you, for example, optimization or things like that.
Yes.
But we don't have any results.
And this is also very relevant to the OBDA or visual knowledge graphs that we said, where you may have a federation of databases underlying, so you need a mediator system. So we also had some work on this area, and you need a mediator system to decompose the query and import fragments, and maybe these fragments can be saved and used in the cache in order to avoid accessing again the external databases.
Okay, thank you.
Just a clarification question. So you have objects and you have geometry and you have features. I can imagine what are the first two, but what are the features?
Actually, feature is everything that has a spatial dimension. So let me go to the ontology.
The features are the objects.
Okay.
Sorry, I said objects.
Geometers. Okay, I think we said features twice. If you mean features here, okay, there is a top thing which is called spatial objects, and it has two subclasses: the geometries and the features. So this is a feature. Building is the feature, it is the feature, so it's your.
Yes. And you compute also intersections between vector geometries and raster, or vector objects and raster objects. How do you do the intersection? I don't know what the output and how they do it.
There is a formal transformation between the raster and of raster cells into the vector world, let's say. So you transform. It depends on how you have defined the transformation. You can either say that it is a point, it's a raster that corresponds to a point in the vector space, or something like that.
Okay. And you operate at vector spaces again.
In the example that we said in on top spatial, yes. In the example of geosparkle, it depends on the implementation, actually. So you can also choose to transform the vectors into rasters.
Dimitri, I have a question actually. If you, so my question is about, if we take your Spark plans, the implementation of the group of stepping stone, and if we take the approach for Sardina for the rasters in, using her approach and then writing the theory, which one would be more efficient? I mean, I know we haven't done experiments, but what is your opinion?
I'm not sure, but it depends heavily on implementation decisions. So I'm not sure about that.
And both for the masterpiece.
Probably, yes. So I guess there is a coffee break now, and
Yes.
the second part of the story will be half an hour.